Okay, so in this video, we're going to be going over the Thermal Physics Part 1 test. This test had both multiple choice questions and free response questions, primarily relating to heat and temperature and pressure and specific heat capacity and latent heat problems, including two object problems. Okay, so do keep in mind as we're going through the test, you should be able to access your test and look at which questions you missed. And the order of the questions on here might be different than the order of the questions on your test. Okay, so just kind of keep that in mind. All right, so question 1 says molecules leave a boiling liquid to form a vapor. The vapor and the liquid have the same temperature. Now, when you see that, if they have the same temperature, that means by definition, those particles making up the liquid and vapor have the same average kinetic energy, because temperature is a measure of the average kinetic energy of the molecules making up, anything. Okay, so the question says, what is the change of the average potential energy and the change of the average random kinetic energy of these molecules when they move from the liquid to the vapor? But if the temperature is the same, that means the average kinetic energy is also going to be the same. However, going from a liquid to a gas, even if the temperature remains constant, it still requires an increase in internal energy. And so if the kinetic energy side is not changing, that means the potential energy side has to change, and it's going to increase. And so the correct answer to this question should be that the average potential energy is going to increase, and the average kinetic energy remains constant. Okay, so that is question 1. Question 2 says a 700 watt electric heater is used to heat 1 kilogram of water without energy losses. The specific heat capacity of water is 4.2 kilojoules per kilogram per Kelvin. What is the time taken to heat the water from 25 degrees Celsius to 95 degrees Celsius? Okay, so a couple things. So first of all, 700 watts is power. Okay, 1 watt is 1 joule per second. And the per second part is important, so just kind of keep in mind that 700 joules per second. Second of all, 4.2 is the specific heat capacity, but look at the unit, kilojoules per kilogram per Kelvin. Okay, and so that means when we go to do the calculation, that's going to be 4,200 joules per kilogram per Kelvin. Okay, so we're looking for time. Q equals mc delta T. And so the mass is 1 kilogram. Specific heat capacity is 4,200. And delta T is going to be 95 minus 25, which is just going to be 70. And so if you do that calculation, let me put this into my calculator and see what answer I get. Okay, so 4,200 times 70. Oops. 4,200 divided times 70 is 294,000 joules. Okay, now it's 700 joules per second. Remember, power is energy over time. And so to get the time, you would have to rearrange this equation, and you would basically have to do the energy, aka the heat in this case, divided by the power. Okay, and so if you do that, you should get 420 seconds. Okay, but 420 seconds is not one of the answer choices. The answer choice, if you convert 420 seconds into minutes by dividing by 60, then you actually get 7 minutes. And that should be the correct answer to the question. So pause it there if you need to look at this more. Okay, so question 3. A sample of solid copper is heated beyond its melting point. The graph shows the variation of temperature with time. During what stage or stages is there an increase in the internal energy of the copper? Okay, so remember, internal energy is basically the kinetic energy of all the particles making up an object plus the internal potential energy of all the particles making up an object. Okay, so in other words, internal energy has two components to it. It has the kinetic energy part and it has the potential energy part. Okay, this has to do with temperature. This has to do with phase, and we've talked about that before in the notes. Now, as we're heating the copper, whenever there is a temperature change, the EK portion of this equation is increasing. Okay, and so during P and R, the internal energy is increasing because this part is changing. Okay, however, during stage Q, just because there's not an increase in temperature does not mean the internal energy is not changing. Because if you keep heating something, even if the temperature doesn't go up, that energy still has to go somewhere. And in this case, it goes to the internal potential energy of the copper. In other words, it goes to phase changing the copper. Okay, and so the correct answer to the question is there's an increase in the internal energy of the copper at every single stage, P, Q, and R. Okay, at again, stage P and stage R, the temperature is going up, so the kinetic energy of the copper particles is increasing. But even during stage Q, the internal energy is still increasing, even though the temperature is not increasing, because that energy, rather than going to the kinetic energy of the copper particles, it's going to the potential energy, and it's going to the phase change. Okay, so it should be all three stages where there's an increase in internal energy. Okay, question 4. A liquid is initially at its freezing point. Energy is removed at a uniform rate from the liquid until it freezes completely. Which graph shows how the temperature T of the liquid varies with the energy Q removed from the liquid? Okay, well, if it's at its freezing point and we take away heat, there's not going to be a temperature change. Okay, because normally, so if you're trying to freeze a liquid, you have to get it to its freezing point, meaning you would have to temperature change it down to its freezing point. But the question says a liquid is initially at its freezing point. That means when you remove heat, the first thing that happens is the phase change. And during a phase change, there is no change in temperature. We talked about that in the notes. And so the correct answer should just be A. The temperature is going to remain constant while the phase change is happening. Okay, so that's question 4. Okay, question 5. What are the units of the ratio of specific heat capacity of copper to specific latent heat of vaporization of copper? So really, this is just like a unit question. If you don't remember the units of something, that's perfectly fine as long as you know how to find it. Okay, remember what you do is you take some equation that has that value in it, and then you just plug units into the equation. Okay, so if you rearrange this equation, you can see the units for C are going to be joules per kilogram Kelvin. Okay, likewise, if you take the equation that has latent heat in it, you can show that latent heat has units of joules per kilogram. So what happens if you take joules per kilogram Kelvin and then you divide by joules per kilogram? Well, it turns out, well, you should have learned this in elementary school, but when you divide by a fraction, what you do is you flip the second term and then you change it to multiplication. Okay, and so joules cancels, kilograms cancels, and what you're left with is you're left with 1 divided by Kelvin, which is the answer to the question. Okay, so that is question 5. Pause it there if you need to look at that some more. Okay, question 6. Boiling water is heated in a 2 kilowatt electric kettle. 2 kilowatt, that's 2,000 watts, by the way. The initial mass of water is 0.4 kilograms. Assume the specific latent heat of vaporization of water is 2 times 10 to the 6 joules per kilogram. What is the time taken for all the water to vaporize? Okay, so Q equals ml, and we have the mass and we have the latent heat. But Q is also a type of energy, and we know this problem has to do with power because it says kilowatts. Okay, and so Q is going to be power times time. And as long as you make the correct substitutions in here, this should be a pretty simple calculation to do. Okay, so you do 0.4 times 2 times 10 to the 6 divided by 2,000. Coincidentally, I should tell you all of the multiple choice questions on here you can do without a calculator, theoretically. 2 times 10 to the 6 is 2 million, and 2 million divided by 2,000 is 1,000. Okay, and so 0.4 times 1,000 is 400. All right, so that is the answer to question 6. Pause it there if you need to look at that some more. Okay, question 7. The temperature of an ideal gas is a measure of the molecule's average kinetic energy. Okay, straight from the notes, that's just a definition question. Definitions are important. Okay, question 8. A solid substance has just reached its melting point. Thermal energy is supplied to the substance at a constant rate, which graph shows the variation of the temperature T of the substance with applied energy E. Okay, so if an object is already at its melting point, if you add more heat at that point, it's not going to change the temperature because all of that heat is going to go to the internal potential energy of the molecules rather than the internal kinetic energy. We talked about that before. We've had questions like this before in this test. Okay, and so that heat is going to go straight to phase changing the solid substance, meaning there's not going to be a temperature change, meaning that the correct answer should be C, because during a phase change, talked about this in the notes, during a phase change, the temperature of an object does not change. Okay, so pause there if you need to look at that some more. Okay, question 9. A mass of water is at a temperature of 290 Kelvin. The specific heat capacity of water is C. Ice at its melting point is added to the water to reduce the water temperature to the freezing point. The specific latent heat of fusion for ice is L. What is the minimum mass of ice that is required? Okay, so this is kind of like a two-object problem. We have water and we have ice. All right, so let's think about this. Qin equals minus Q out. And we have heat going into the ice. Okay, and the ice is at its melting point, and so the only thing that would ever happen to the ice would be a phase change. And so on the Qn side, we would just have the mass of the ice times L, the latent heat of fusion. On the right side, we have minus Q out, and what's going to happen is the other object is the water, and the water is going to cool down. Okay, it's currently at 290 Kelvin. We want to get it down to its freezing point. So for this question, you have to know a couple things. Number one, the freezing point of water is 0 degrees Celsius. Number two, you need to understand that you need to convert that to Kelvin because this temperature is in Kelvin. So you add 273 to convert from Celsius to Kelvin. This is Ti, and we want this to be TF because we want to cool it down from 290 Kelvin to 273 Kelvin. So we have minus MC, and then the delta T would be 273 minus 290. That difference is 17. Actually, it's negative 17, and negative 17 is going to cancel out with this negative sign in the equation. And so we get M ice times L equals 17 MC. And so M ice is going to be 17 MC divided by L. Okay, and that's the answer to question 9. Pause it there if you need to look at that some more. Okay, question 10. Energy is transferred to water in a flask at a rate P. The water reaches boiling point and then P is increased. What are the changes to the temperature of the water and to the rate of vaporization of the water after the change? Okay, so let's see. Energy is transferred to water at a rate P. Okay, the rate at which energy is transferred is power. Okay, that's why they're calling it P, by the way. Rate of energy is power. The water reaches boiling point and then P is increased. Okay, so in other words, we increase the power or the number of joules per second of heat that we're adding to the water. But look, if it's at the boiling point, even if you increase P, what happens to the temperature during a phase change? Well, the answer is nothing. During a phase change, the temperature doesn't change. We talked about that several times already in this video. Okay, so that means the temperature should be unchanged. However, the rate of vaporization would increase because obviously if you're adding heat at a faster rate, it's, the internal energy is going to increase faster. That energy just shows up in a phase change. Okay, so the vaporization is going to happen faster. So pause it there if you need to look at that some more. Okay, question 11. For two objects to be in thermal equilibrium, they must be at the same temperature. That's just from the definition of thermal equilibrium. All right, so now we get to the free response questions. Okay, so question 12 is a 6-point question. It says this question is about change of phase of a liquid and latent heat of vaporization. A says a liquid in a calorimeter is heated at its boiling point for a measured period of time. The following data are available. Okay, and it says use the data to determine the specific latent heat of vaporization of the liquid. Notice, by the way, that the liquid is already at its boiling point, and so when we add heat to the liquid, that heat is not going to change the temperature of the liquid at all. It's going to just go to phase changing the liquid. Okay, I should also point out that this liquid is not necessarily water. For some reason, a lot of people made that assumption, but I digress. All right, so we know that Q equals M times L, and we know that P equals Q over T. And so if we combine those two things, we have, 34 joules per second times, in this case, 250 seconds. 2.5 times 10 to the 2 is 250. And that's equal to the mass of the liquid that's boiled away times L, the latent heat. Okay, and so all we need to do is multiply and divide, and we will be done with part A. And honestly, people did pretty well on this question. And of course, I should point out, in case it's not clear, that you probably have different values for your question, and so your exact answer might be different than mine, but that's okay. Okay, so the answer I get is something like this, 223,684 joules per kilogram. So pause there if you need to look at part A some more. Part B says, state and explain one reason why the calculation in A will give a value of the specific latent heat of vaporization of the liquid that is greater than the true value. Okay, so the first answer to this question, what is the reason why the value of the calculation might be different, is because that you're assuming that all of the heat goes into the liquid. In other words, you're assuming that there's no heat loss to the surroundings or to the container itself. Okay, so that's one point. Okay, the second point is using that fact to explain um, why does the calculation give a value that is greater than the actual value. Okay, and the reason for that is because basically, again, the actual value for Q going into the liquid is actually less than what we're assuming. So we're assuming it's 34 joules per second, but in actuality, it's probably less than the 34 joules per second because some amount of that power or some amount of that heat is going to go to the surroundings. Okay, and so we're basically in this calculation, we're overestimating the amount of heat going into um, the liquid. All right, so some people got the first part for explaining that maybe the heat goes to the surroundings, but almost nobody got the second part, which is answering the second part of the question. Okay, why is the value of the latent heat greater than its true value from the calculation? Okay, so that was B. And then C, there seemed to be a lot of confusion about C as well. The liquid from the previous problem is dumped out and replaced with 3.8 times 10 to the negative 2 kilograms of the same liquid. By the way, this problem is talking about a liquid. A bunch of people, for some reason, assume that it's like water, and they assume that the boiling point is like 100 degrees Celsius. That it doesn't say anything like that in the problem. Okay, so the liquid is dumped out, replaced with the same liquid with the same specific heat capacity, the same latent heat, different or same mass actually. The initial temperature of this liquid, it says in the problem, is 81 degrees below its boiling point. The heater operating with the same power rating as below takes 55 seconds to heat the liquid back up to its boiling point. Okay, if it's 81 degrees below boiling point, that means the delta T to get back to the boiling point is 81 degrees Celsius. Think about that for a second. It doesn't say that the temperature is 81 degrees Celsius. It says it's 81 degrees Celsius below its boiling point. That means the delta T is going to be at 81. Okay, and so Q is going to be mc delta T. We have the mass. We don't have C, but delta T is going to be 81 degrees. And again, at this point, I saw a lot of people trying to do like 100 minus 81. 100 degrees has nothing to do with this problem. This is not water. This is some unknown liquid. Okay, so a bunch of people were just trying to like make up stuff about this problem that wasn't true. And on the left side, Q is going to be the power, which I think was 34, times the time, which is given as 55. Okay, so I'm not going to finish out the calculation. You can do the rest on your own. If you get to this point, you're just dividing both sides by two values to get C by itself. Okay, but that's how you should approach this problem. Pause it here if you need to look at this some more. Okay, question 13, 9-point question. This is the biggest calculation question on the test. Okay, so a block of ice at an initial temperature of negative 30 degrees Celsius is heated up until it becomes water and completely boils away, and a bunch of values are given. Okay, part A says, calculate the amount of thermal energy required to turn the entire block of ice into steam at 108 degrees Celsius. All right, so this is a 3-point question, but it's a pretty straightforward calculation because we did problems like this in class. All right, so we have the mass of the block is 35. Okay, so the block starts at negative 30 degrees Celsius. As you add heat to it, the first thing that's going to happen is it's going to temperature change up to its melting point, which is 0 degrees Celsius. Okay, so we have mc delta T, the specific heat capacity for ice is 2030, that's given in the problem. The delta T would be positive 30, because it's going from negative 30 to 0, plus, once it gets to the melting point, it's going to melt. And so plus, we have to have some heat for that. So we have ml, we have an ml term, 35 times 3.4 times 10 to the 5, plus, now that it's melted, we have liquid water, and that liquid water is going to go from 0 degrees up to 100 degrees Celsius. It's not going to go past 100 degrees Celsius because 100 degrees Celsius is the boiling point of water. And so we have mc delta T for the water stage. It's going to be 3,500 times 4,200 times delta T, which would be 100. Once we get it there, we need to phase change it into steam. And so that's going to be 35 times the latent heat of vaporization. And then once you turn it into steam, then we need to temperature change it from 100 degrees Celsius to 108 degrees Celsius. And so we have different terms in this problem. Specific heat capacity of steam is 2000. And then the delta T is going to be 108 minus 100, which is just 8. Okay, and I'm not going to put all this into the calculator because there's no point. If you get to this part, then I'm assuming you can type those numbers in correctly. Okay, the trick to doing this problem is understanding that you have these, 1, 2, 3, 4, 5 different terms. And as long as you set the terms up correctly, then you should be able to do the calculation correctly. So pause it there if you need to look at part A some more. Okay, so now let's look at B. Okay, B says, the block of ice is tossed into a swimming pool filled with 3,000 kilograms of hot soup, because why not? And that soup has a specific heat capacity of 3,700. And the soup has an initial temperature of 90 degrees Celsius. B1 says, calculate what the temperature of the soup would be once the ice block reaches its melting point. So this is a two-object problem. Okay, so I'm going to just kind of write down values. For a two-object problem, we have Qin equals minus Qout. Now, heat is going into the ice, and it's going out of the soup. All right, so kind of keep that in mind. So on the left side, I basically have the ice. Now, B1 says, what is the temperature of the soup once it has reached its melting point, once the ice block has reached its melting point? So that means the only thing happening to the ice block on the left side is a simple temperature change. And what happens to the soup is also just a simple temperature change. Okay, so we have 35 times 2030 times, let's see, it started at negative 30 degrees Celsius and its melting point is 0 degrees, so that delta T would be 30. And then on the right side, we have the soup. We have a mass of, I think it's 3,000. Let me just check. Yeah, 3,000 and 3,700. Okay, so 3,000 times 3,700 times T final minus 90. So I'm going to type this into the calculator. You get 35 times 2030 times 30. So you get this number on the left. And then on the right, if you distribute out this term, you get negative 111,000,000 TF plus 90 times that. Okay, so plus 999,000,000. And I'm assuming that you can correctly rearrange this on your own. That it's a positive value, by the way, because this negative sign and this negative sign cancel each other out, in case you wanted to know why that was. And let's see. The answer you should get, at least with the values I have, is 89.8 degrees Celsius. Okay, so this is not thermal equilibrium, but this is just to get the ice block to its melting point. Okay, at that time, the soup is cooled down by basically like 0.2 degrees. Not a lot, but a little bit. Okay, so pause there if you need to look at that some more. Okay, now the next part of the question basically asks, what is the final temperature of the ice, or the final temperature of the soup once the block of ice has completely melted? Okay, so this is B2 that I'm about to do. So for B2, I'm going to erase some of this. So for B2, now we are doing not just a temperature change, but also a phase change. So you have an MC delta T part plus you have an ML part. Now that is assuming that you keep the initial temperature at 90 degrees, which you don't necessarily have to. What some people did is some people thought to themselves, okay, so I already know what the temperature of the soup is going to be once it's cooled down by 30 degrees. I can just write the ML part by itself on the left side, and then I can change the initial temperature from 90 degrees to 89.8 degrees because I already know that that's going to be the final temperature just from the 30-degree temperature change by itself. So you can also approach the problem like that, which I'm actually going to do just in the interest of having less to write. Okay, so now the soup is basically starting at 89.8 degrees. That's what the temperature was at the end of the last problem. And now we want to know what is it going to be for this phase change. All right, so we have 35 times, let's see, the latent heat of fusion. I believe the value it gives is 3.4 times 10 to the 5. Okay, so 3.4 times 10 to the 5. And that's equal to all of this mess. This value is going to be the same. This other term, though, I'm going to multiply the 3,000 times the 3,700 times the negative 89.8. And again, as I type this into my calculator, I do want to be clear that you didn't have to do it this way. You could have just started from scratch and kept the initial temperature at 90 degrees, and there would be nothing wrong with doing that. Okay, so on the left side, 35 times 3.4 times 10 to the 5. We have 119, right, 1,190,000, something like that. It's hard to count zeros. Okay, but if you set this up correctly and you get TF by itself, let's see what you get. Okay, so you should get TF equals 88.7 degrees Celsius. Notice that these temperature changes are relatively gradual. That's because you have a really big mass of soup. Okay, so even though it's a pretty big chunk of ice, it's also like way more hot soup. So the temperature is changing, but it's not changing by a lot. Okay, so that would be for B2. Okay, now B3 is asking, what about the thermal equilibrium? Okay, so again, at this point, either you can start over from the very beginning, you can start at the initial temperature of 90 degrees, and then on the left side, you would have three terms. You would have an MC delta T part for the ice, you would have an ML part for the phase change, and then you would have another MC delta T part for the melted ice reaching thermal equilibrium with the soup. Okay, so you could do that, but just to save on space, I'm not going to do it like that. I'm actually going to reset the initial temperature from 89.8 degrees to 88.7. In other words, once the ice has cooled down and melted, the soup now starts at a temperature of 88.7 degrees. And so if I treat it like that, what that allows me to do is instead of having three terms on the left side, now all I have is an MC delta T term on the left side for the melted block of ice. Okay, and so the melted block of ice is going to have a mass of 35, it's going to have a specific heat capacity of 4200, and it's going to have a final temperature of T final minus its initial temperature, which is 0. And so rather than write T final minus 0, I'm just going to write T final. All right, so 35 times 4200 is 147,000 TF. Now all I need to do is combine like terms. I do need to distribute out this 3,000 times 3,700 times 88.7, and I get a big ol' number over here. But if I add this TF term to both sides and then divide, I can get the correct answer. Okay, so give me just a second. I'm typing this big number into my calculator. So 9845700000, and I get a final temperature of 87.5 degrees Celsius, and that is it for B3. And again, your values are probably going to be slightly different, but the way to approach the problem is the same. Okay, so pause it there if you need to look at that some more. And again, my approach to doing this problem for you is not the only approach. You also could have started from scratch, and then you would have three terms on the left side, and you would have kept the initial temperature at 90 degrees on the right side. I just decided not to do it like that, just to have less stuff to write. Okay, last problem. Okay, question 14. A piece of copper is held in a flame until it reaches thermal equilibrium. The time it takes to reach thermal equilibrium will depend on the thermal capacity of the piece of copper. Outline what is meant by thermal equilibrium in this context. This question is not asking what thermal equilibrium is. It's asking what does thermal equilibrium mean in this context. Okay, well, the piece of copper is held in the flame until it reaches thermal equilibrium. In this context, that means the copper is going to reach the same temperature as the flame. That's it. That's the answer for A. Okay, the copper and the flame are going to have the same temperature because they're in thermal equilibrium. Okay, that's all you had to say for A. For B, the piece of copper is transferred quickly to a plastic cup containing water, and they give you some information, and they ask you to find the temperature of the flame. A lot of people did pretty well on this question. This is a two-object problem that just involves the copper and the water, but it's a relatively simple one because there's no phase changes. So Q in equals minus Q out. On the water side, we have the mass of the water, which is 0.36, the specific heat capacity of the water, which is 4,200, and the delta T of the water, which is given right here as 30. And then on the right side, we have minus Q out, so minus 0.19 times specific heat capacity of copper, 390, times the final temperature of the copper is given as 308, and the initial temperature of the copper is the same as the temperature of the flame. So when it asks you to find the temperature of the flame, that's going to be the same as the initial temperature of the copper. And your answer that you get really just depends on which version of the test you have. And so I will tell you what it should be with these particular calculations. Give me just a second. So 0.36 times 4,200 times 30. Okay, and what you should get is, let's see, approximately 920 degrees with these values. 920 Kelvin. And again, your answer might be bigger, might be smaller. It just kind of depends on which version of the test you had. Okay, so that is it for this test. As always, please let me know if you have any questions, and I'll see you guys in the next video.